Let us discuss here two theorems on subsequences. The first one, we have it here, says that a sequence converges to some p if and only if every subsequence of the original sequence converges to the same p. Okay? This is actually very useful because if we have two subsequences that converge to different limits, then the sequence cannot converge. So if we have two subsequences that converge to different limits, the sequence cannot converge. For example, let's say we have the alternating sequence 1, -1, 1, -1, 1, -1, and so on. We can apply this theorem and say, well, because we have the sequence, let's say Pn1, let's use a different letter. So let's use Yn, which is always 1. Okay, so this will be the subsequence Yn, which is always 1. And we could have the Yn prime, which is always -1. Okay, so for these two subsequences, the limit of the first would be 1, the limit of the second would be -1. So the original sequence Pn has no limit. Okay. For the second theorem, we have it here. We have a sequence in a compact metric space. And then the theorem says that there is some subsequence that converges to a point of x. Okay, whenever we have a compact metric space, there is some subsequence that converges to a point of x. Now, here, there is an important consequence that says that every bounded set in Rk contains a convergent subsequence. Okay, and this follows because whenever a set is bounded in Rk, let's say that E contained in Rk is bounded, that implies that E is contained in a K cell, that this is a rectangular prism in Rk, and we saw that these were compact. We saw this in a previous video. Okay, another theorem says that if we have any sequence that we take in this set E, okay, so we take Pn contains in this set E, then it's going to be in a compact metric space, and then there is some subsequence Pni that converges in X. Okay, the theorem says that there exists a sequence that converges. So, how do we prove the theorem? Well, actually, before we go into the proof of the theorem, I want to mention something a little more advanced. There's a more general version that says that a metric space X is compact. We saw the definition of compactness using coverings, but when we have a metric space, the compactness is equivalent to every sequence of points in X having a convergent subsequence. Convergent subsequence to a point of X. Okay, sometimes this is called the second property. Sometimes it's called sequential compactness. Okay, we are not going to see the proof of this equivalence because it's as I said, it's a little more involved. Proof of theorem 2. Let's take the range of the sequence E. Remember, the range of a sequence is the set of points that appear in the sequence. Okay, so there are two possibilities. The first one is that the range of the sequence is finite. For example, this happened when we had the alternating sequence or sequences that involve jumping among a finite set of points, okay? Even if that set is very large. If this is the case, then there is a point P in E and the sequence in I, okay? This sequence, this is an increasing sequence, and this is such that Pn1 equals Pn2, Pn3, and so on, and all of them are equal to the limit. Okay, think about this for a moment. If you have finally many choices for a sequence, okay, the sequence is jumping among finally many choices. At some point, you need to pass through one of those choices infinitely many times because the sequence has infinitely many repetitions. So, well, at least one of the points you will have to pass over and over and over and over. Okay, so that is going to be a limit point, as we are seeing here. And then what we have found actually is a subsequence we have found a subsequence that converges to P, which is a point in E. Okay, and this is contained in X. All right, and this was the easy case, but the other case is not difficult. The other case is when E, the range of the sequence, is infinite. Okay, we could say that this is an actual sequence. So for example, this would happen in the sequence 1 over n, that we have an infinite range. But anyway, so because E is an infinite set, we saw that an infinite set must have a limit point. Okay, let me open a new line. It has a limit point P in X. Okay, this is the fact that E is an infinite set. Now, we can choose, because we know there is a limit point, okay, we can choose an index n1 such that the distance from P to Pn1 is less than 1. And you may be wondering, how do we know there is some element in the sequence that is within distance 1 of P? Okay, this is by definition of limit point. P is a limit point if and only if, by definition, every neighborhood of P contains some element of E, at least one that is different from P. Okay, because E is the range of the sequence, every element in E is going to look like P and something. Okay, so that means that there is, when I take the neighborhood of radius 1 around P, there is some point. That point, I call it Pn1. And I can do this as many times as I want. Okay, here, let's do one more. I will choose n2 such that the distance from P to Pn2 is, guess what? Less than 1/2. This is again by the definition. I'm taking a neighborhood of radius 1/2 around P. And there is some point in E, which being the range of the sequence, says that the point has to be of the form Pn something. And I just do this over and over. And in general, at step I will find a point Ni such that the distance from P is going to be 1/I. Here, this I is just an index, nothing to do with complex notation, okay? Now, see what happens here? So we have shown that, basically what we have shown is that the sequence, the subsequence P and I converges to P, okay? This is because for whatever epsilon I pick, okay? Whatever epsilon you give me, I will be able to find some I such that 1/I is less than that epsilon you gave me. Okay, so from here we get the definition of convergence for the subsequence.